Hello everyone and welcome to the first live session inaugurating the 7th International Electronic Conference on Sensors and Applications, also known as ECSA-7. This conference has been organised by MDPI and the journals Sensors and Chemosensors. I would like to thank all speakers and all participants for joining us today. From today and up until the 30th of November, you'll be able to read and comment all the authors' submissions presented for the conference and also enjoy some live sessions. In order to do this, please look at our webpage for more information. I would also like to remind everyone that this webinar is being recorded and that we also have a YouTube live stream today. The recording will be posted as soon as possible on the webinar's webpage for everyone to watch or rewatch. Today, Dr. Stefano Mariani is chairing the session. Dr. Mariani received a master's degree in civil engineering in 1995 and a PhD degree in structural engineering in 1999. Both degrees are from the Politecnico University of Milan. He is currently an associate professor at the Department of Civil and Environmental Engineering at the Politecnico University of Milan. He was a research scholar at the Danish Technical University in 1997, an adjunct professor at Penn State University in 2007, and a visiting professor at the Polytechnic Institute of New York University in 2009. He is a member of the editorial boards of Algorithms, International Journal on Advances in Systems and Measurements, Inventions, Machines, Micro and Nanosystems, Micro Machines, and of course, Sensors. He has been a recipient of the Associazione Carlo Maddalena Prize for graduate students and the Fondazione Confagonieri Prize for PhD students. His main research interests are the reliability of MEMS that are subject to shocks and drops, the structural health monitoring of composite structures through MEMS sensors, numerical simulations of ductile fractures in metals, and of quasi-brittle fracture in heterogeneous and functionally graded materials, extended finite element methods, the calibration of constitutive models via extended and sigma point Kalman filters, and last but not least, multi-scale solution methods for dynamic delamination in layered composites. Thank you, Stefano, and I hand you the floor and the live session can officially start. Enjoy.
Okay, thanks a lot. Thanks for your kind introduction. I will say first a few words to thanks all the contributors for the excellent papers they sent to us for review, and all the people today here connected to attend this study section of our ECSA conference. Let me say a few words about this electronic conference. So as you see, this conference is an electronic one. So that means that it was born as an online conference. So we are facing now big problems related to pandemics, and we see that many conferences, if not delayed or if not canceled, they're moving to an online version. So we can say that this conference was instead born this way. So at the beginning it was rather small, and during the time it grew up, and we are very happy that today, this year, we received more than 100 contributions accepted. So we kept a very strict review process for all of them. And so what I can say today is that I'm really happy and I welcome you to this starting session related to Chemo and Biosensors. So today we have the 4 presentations you see here listed. They were selected on the basis of the quality of the contents. So I'm pretty sure that we will have a very exciting session attending the presentations. I would like to invite all the attendees if they are willing to raise questions, because we see that we have 20 minutes for each presentation. So we will have time at the end of each single presentation to raise questions. So if you want to raise, please try to write your question into the chat, or if you prefer, you can even raise your hands. So we will try to let you have the word in order to ask the question personally. At the end of the session, I think we'll have time in order to have a common discussion related to all the contributions. So keep in mind that at 11, we will have to follow the keynote lecture to be delivered by Benedetto Vigna, who is Vice President of ST Microelectronics. Since we will have kind of 30 minutes for the discussion and break, so we'll have time to discuss. So I think that even if we are a bit early, it's time for me to stop and to give the stage to Dr. Hontañón for her presentation. And so Esther, thanks for being here. Thanks for your contribution, and let's have it started.
Okay, thank you very much.
So I start sharing my screen, so now you can.
Okay, thank you. Okay, so good morning. My name is Esther Hontañón. I belong to the Spanish National Research Council, and I'm going to give this talk on behalf of my colleague Sergio Massa, who was finally not able to attend this session today. And the title of my talk is the Electrospray printing of graphene layers for chemiresistive gas sensors. This is the content of my presentation. First, I will say a few words about the motivation of this work. As everybody knows, the wireless sensor networks is an emerging technology that is supposed to be the most promising one in order to attain the most accurate and with the highest spatial and temporal resolution on the quality of the environment we live in, and in particularly the quality of the air we breathe. And this technology poses great challenges to the gas sensing technology, since for it to become a reality, it is necessary to develop sensors that must fulfill a number of requirements. First, they have to be of a very small size, in the micro or even in the nano scale, because the idea is to implement or to assemble and integrate a large number of those sensors in very small wearables and personal devices. Secondly, the next generation of gas sensors must be easy and affordable to fabricate and to manufacture, and also they should consume as less power as possible, ideally not power at all. There are other requirements in terms of detection or sensing performance, because for air quality applications, for instance, the gas sensor must be able to discriminate between a large number of toxic air pollutants present in the air that are most of them present at ppb level. And one of the most promising technologies or suitable technologies to face this challenge and to fulfill the previous requirements are the gas sensors of the resistive type based on metal oxides. And this technology is considered to be promising in this regard because mainly of the high potential for miniaturization it offers. The present state of the art of these metal oxide gas sensors is depicted in the left image on the slide. And these are these microsensors, which are basically micro electromechanical systems, which consist of a substrate of silicon, which is subjected to a number of processing steps, which are multiple steps. And in order to print or to practice in the top surface of the substrate, all the main components of these sensors. This is one of the advantages, the potential for miniaturization, but there are also some disadvantages. The main one is that these metal oxide gas sensors operate typically at high temperatures. Normally, they reach the maximum sensitivity of response to specific gases at temperatures well above 300 centigrade degrees. So it means they consume relatively high power as compared to other sensing technologies already available in the market, like for instance, the electrochemical gas sensors. Also, they have the disadvantage that the fabrication is costly because some of the processing steps also consume a lot of energy because they are performed under high steam conditions like high temperature or vacuum. So they demand the use of costly equipment which consume energy. And also the scalability is limited by the size of the silicon wafer, which is the starting point, and which maximum size nowadays does not exceed 30 centimeters. So there are some disadvantages too. So the research in the last decade has, let's say, focused on the development of new gas sensors, which are able to operate at low temperatures, generally below 100 centigrade degrees, even room temperature, in order to overcome all these problems of the metal oxide gas sensors. And the research has been focused has followed two approaches. On one side, it has been intended to explore further the possibility and the potential of the metal oxides to operate at low temperature by means of the nanotechnology. In the previous generations of metal oxide gas sensors, the sensing layer was what is called the thick or thin film, which is a compact or relatively compact film. And these are basically the type of film sensing layers that are used in the commercial metal oxide gas sensors that are currently available in the market. But the nanotechnology allows first to generate or to produce, to synthesize metal oxides in nanoforms or nano elements of any dimensionality, as you can see on the slide. And these nano elements can be used also by means of the nanotechnology to construct layers on the surface of the substrate, which have with a very well control of the morphology and the final structure. And one of the characteristics of these nanostructure layers is that they are highly porous. So it means that they allow the gas to access a huge surface of the metal oxide and to contact a lot of active site at the surface of these metal oxides. And also facilitates the entrance and the release of the gas from the sensing layer. So basically the idea is that the idea behind this research is that by optimizing or making a proper engineer of this graphene, of this metal oxide nanostructure layers, it would be possible to reach a good sensitivity and also to reduce the response and the recovery times of these sensors to levels that are acceptable for gas, for air quality applications, for instance. And the other approach consists in avoiding, let's say, the metal oxide and exploring the potential of a new family of materials, mostly 2D materials, which are the leader is the graphene, but of course there are some others which are emerging in the last years. And the graphene is the most investigated one so far. And the graphene, as you know, is not a unique material, it's a family of materials. And there are different types. There are three main types. The pristine graphene, which is the purest and also has no defects, but it has some disadvantages for gas sensing because there are carbon atoms on the corner of this hexagonal structure inert, so it's necessary to modify or functionalize the surface of these graphene layers to make them reactive to the gases. The other disadvantage is that the scalability of the production of pure pristine graphene directly from graphite is not affordable right now, and one can only produce small amounts. Instead, we have other member of the family, which is the reduced graphene oxide, which is produced by an alternative method. And it has some more advantages with regard to pristine or graphene oxide. And the advantages are that, first, the reduced graphene oxide, the production can be easily and affordably scale up. So it's possible to produce large reduced graphene oxide in large amounts. And secondly, the production process itself allows tanning and adjusting the properties of the reduced graphene oxide to make it optimal for the specific application behind. So this is the type of material we have used in our work for the preparation of these gas sensors. And the materials we have used, as I said, is we start from a precursor solution of reduced graphene oxide in isopropyl alcohol with a concentration of 0.1 milligrams per milliliter. And the material, the reduced graphene oxide, is a commercial powder that is produced by Avalonix, which is a graphene manufacturer in Norway. And after characterizing the powder with a number of spectroscopy techniques, it came out that the material has not many defects, it's not very defective, but has a lot of oxygen groups on the bonded to the carbon on the layers. So it's expected that this material should have some reactivity to gases. Other properties we have measured are the specific surface area, electrical conductivity, carbon to oxygen atomic ratio, and also the average number of the stack layers, which is estimated to be around 7. Also, we found that the isopropyl alcohol was the best solvent because it leads to the best, highest, and more stable dispersions of RGO in the suspension. As a substrate, we have used a multi-sensor platform consisting of 4 interdigitated electrodes of copper, which are screen printed on the surface of polymer, which is commonly used in printed circuit boards. And the area of the active surface of these interdigitated electrodes is in the order of 7 millimeters square. This is a layout of the experimental setup we have used for Electrospray, the RGO dispersions. We put a few millimeters of this RGO dispersion in the syringe, and these are with the help of a pump fed to the through a capillary tube to the tip of a metallic needle at a constant rate, and a high voltage is applied on the metallic needle, and in front of that we put the electrode on which the sensor substrate is supported, and at a given distance from the needle tip. And we have to optimize, decided to optimize the processes parameters of the Electrospray in order to fill 3 major requirements. The first one is that the dispersion, because we are not using here surfactant or dispersers to ensure the long-term stability of the dispersion, because we don't want to affect the sensing performance of the base material, which is the reduced graphene oxide. So in this first work, we have not used this surfactant. And so then the dispersion must remain stable during the time it takes to prepare the sensors, which was in our experiments vary between 5 and 20 minutes. Secondly, the Electrospray operation mode should be also stable as well. So this is attained by optimal tuning of the dispersion feed rate and also the applied voltage. And finally, the solvent must evaporate from the droplets, Electrospray droplets, before they reach the substrate in such a way that only the graphene or the reduced graphene oxide, the flakes that are suspended or dispersed in these droplets, deposit on the substrate in absence of liquid at all, because the liquid normally leads to very inhomogeneous deposits. So we avoid deposition of liquids on the surface of the substrate. Here you can see the different regimes that one finds once the feed rate of the dispersion is set to a given value and you start increasing the voltage applied to the needle, the Electrospray grows through a variety of operation regimes and transitions, starting from a very highly unstable one, which is this pulsating cone jet, and then it reaches this more stable continuous cone jet mode. And by increasing further the voltage, this kind of jet starts moving around the cone, and at some point you get this kind of tilting of this jet, and finally the atomization or appear of many multiple jets. We have found that in order to attain homogeneous and uniform deposits of RGO on the substrate, it's necessary to operate the Electrospray in the continuous conduit, which is the most stable one. Here you can see how the RGO deposit look like after Electrospray, and you can see what we finally found is that the size of the deposit of RGO on the surface of the substrate depends on basically not only, but is mostly determined by the separation distance between the needle tip and the substrate. So we start performing experiments at relatively long distances in order to cover the surface of the 4 sensors simultaneously in only one step. And in these experiments, the needle was centered and pointing to the center of the substrate. And you can see here that the size of this spot basically covers the diameter of the substrate. When you reduce the distance, then you get smaller spots. At some point, the spots are so small that they approaches the size of the individual sensor. So we moved to another type of experiment in which the needle was entering and pointing to the center of the individual sensors. And this is in this one, you can see that the distance is the same, but in the first one, the needle was pointing to the center of the substrate, and in this way we perform for the position test entering at any of those. And in this case, there was some overlapping of the deposit, so that's the reason why it's not fully uniform. But when you reduce this distance further, you can see that the size of the spot approaches the size of the interdigitated electrodes, and even you can get even smaller. You can see also that the surface density of the RGO in the deposits increases when reducing, because of course the size of the spot is smaller, but the amount of material that has been delivered and dispensed is the same. So we start also the process is rather repeatable, as you can see in the image on the right hand side. And we start performing, let's say, gas measurements with the different sensor substrates. And then we observe that this case was the first one in which the 4 sensors, the resistance of the 4 sensors went down to values within the measurement range. And also they show acceptable sensitivity to the target gases, nitrogen dioxide and ozone, at sub ppm level. So these are the results I'm going to show you. In this case, for instance, we observed that because maybe the surface density of RGO was too low, and also in some cases the cover of the whole surface was only partial, was you get sometimes that the resistance of the sensor is not within the measurement range, or the signal is very weak, or there is a lot of noise. So this was the first one who really succeeded. And these are the results I'm going to show you now. Just the layout of the facility we use to perform the gas measurements, which is a standard one. We use mixtures of gas mixtures of known composition. For nitrogen dioxide and carbon monoxide, one can use this gas cylinder of calibrated mixtures. In the case of ozone, because it's quite unstable, it cannot be stored. So then you have to produce in situ, and we use a commercial ozone generator. The gas is coming from the ozone generator or from the cylinders, is mixing a gas mixing unit with the clean air coming also from the cylinder, and then one can adjust the desired concentration of the target gas in the mixture. Also, the gas, eventually the gas can be passed through a bubble in order to increase and to adjust the humidity of the gas. And the system is fully automated and is controlled from a program based on the LabVIEW software. Here are the first results regarding the gas detection. First, I have to say that we try to perform also measurements with carbon monoxide, but with this particular sensor I mentioned before, it was not possible. It was not able to detect CO up to 5 ppm, which is a concentration range relevant for air quality applications. This can be a good point or a bad point, depends how you look at the result, because it's not able to detect CO. We can say it's more selective to oxidizing gases, let's say. So the interferences with the CO and maybe other non-oxidizing gases is less, or there are not interference at all. In the case of the oxidizing gases, nitrogen dioxide and ozone, we observe that first the RGO behaves like a p-type semiconductor, because the resistance decreases when the gas is passing through over the sensor, and the sensitivity is also higher for ozone than for nitrogen dioxide. And also the main point is that we observe that the recovery recovery time is extremely long. For the nitrogen dioxide, even a bit worse than for ozone. And also in this test, we used dry air, which the gas mixture did not pass through the bubble, but still in this case you get a very high humidity level, let's say less than 5%. So now we studied the effect. Then we studied the effect of the air humidity on the sensing performance of this sensor, based on this Electrospray reduced graphene layers, and we observed that the humidity has 3 major effects. First, the resistance increases. In the top figures, you can see the evolution of the dynamic resistance of the sensors, of one of the sensors, as a function of for different levels of concentration of the gas in the mixture, and also different levels of air humidity. And you can see that the humidity, by increasing the humidity, the resistance of the sensor increases too, but also the sensor response. Here you can see the sensor response to different levels of nitrogen dioxide and different levels of air humidity. With the humidity, for all the sensors saw an increase of the response, but in any case, it was not none of them was able to detect levels of nitrogen dioxide below 200 ppb. In the case of the ozone, the situation is the same, and the responses are higher too. And in this case, we were able to detect even 50 ppb with a response of 1%. And the reason why this is not increasing continuously with increasing the concentration is, we suppose, because even if the recovery time, you can see that increases or reduces with the level of humidity in the air, the recovery was not full even at the highest humidity. So it means that after the cycles, there should be some, let's say, accumulation or saturation of gas in the sensing layer, and it forces or makes that the response by increasing the concentration is not increasing continuously, but reaching a kind of plateau. So then we can say that the effect of humidity is, I say, to increase the resistance of the sensor, to increase the response of the sensor also to the two gases, and to reduce the recovery time of the sensor. Still, we investigate the possibility to reduce further the recovery time of the sensors by illuminating the sensor with UV irradiation coming from a LED source. And we found that indeed the UV irradiation has a very positive effect, because it was possible by optimizing the time the UV light is acting on the illuminating the sensor during the gas desorption phase or sensor recovery phase. It was possible to recover the baseline and also to see the stability in the response. This you can see here in the response for the different cycles. And in the first cycles, there was no, the sensor was not illuminated and irradiated. So then you can see this decrease in the sensor response. Once the UV is activated during the recovery phase or the gas desorption phase, the sensor or the sensor baseline or the resistance baseline is recovered, and then the response is much more stable. And we reach a value of about 4% for 100 ppb of ozone. So just to conclude, I will say that we have prepared sensors by electrospray of reduced graphene oxide dispersions. Yeah, we have characterized the graphene layers for the detection of nitrogen monoxide, ozone, and carbon monoxide. We have found that the detection limits with this specific sensor I mentioned are not sufficient or low enough for air quality monitoring, since they should be below 50 ppb. Is not sensitive to CO, which makes it selective somehow. And the sensors have very long recovery times at this room temperature of the experiments, of course, and all the sensors are worked at room temperature, because this is the goal of using these graphene materials. But decreases with increasing the air humidity, and can be even increased further by irradiating the sensor with UV light. With regard, with regard to the electrospray, we have seen that it is possible to obtain homogeneous deposits and reproducible too by operating the electrospray in the most stable continuous conjugate configuration. So it means that the feed rate and the flow and the voltage should be finally adjusted in order to get this reading, because further small deviations from the optimal voltage led to very produces or causes drastic changes in the deposition pattern of the RGO. So the size of the spot, as I said before, is determined mostly by the distance between the tip and the substrate, but the deposition pattern itself, as I said, is more determined by the operation regime, which depends on these two main parameters: the feed flow rate and the applied voltage. And in the future, what we intend to do is several things. We intend to use surfactant or dispersant in order to guarantee the long-term dispersibility of the RGO. And we also check if they have or not effect on the sensing performance of the sensors. We also would like to investigate other types of reduced graphene oxide. There are many available in the market with different levels of reduction. And so we have to investigate other potential RDO types. And also we would like to find some kind of dopants for this RDO and others in order to detect the carbon monoxide and other non-oxidizing gases, like for instance, reducing gases, like for instance, ammonia and so. And also we would like to further explore, further investigate the effect of the UV light on the recovery time mainly, and also the sensitivity, because there are some parameters that we have not yet sufficiently assessed, like the wavelength of the light and also the intensity of the light. They can affect in a very significant way the performance of the sensor in terms of sensitivity and recovery time. So we want to try with another UV light LED sources different from the one we use in this work, and also with a different range of power. And this is all from my side, and I close my presentation. I thank you for your attention.
Thanks for your presentation. I think we are almost running out of time, so we have maybe the time for a very quick question. Is there anyone willing to ask anything? Alberto, yes, please. Sorry, Alberto, you're mute.
Sorry.
Okay,
now it's okay. Okay, sorry. Thank you for your presentation. It was very interesting. I'm just curious about the effect of humidity and temperature. I wonder why the sensitivity increases with humidity. And I would like also to know if there is an effect with temperature, since your tests were carried out at ambient temperature.
Well, in fact, we have not yet tried to figure out we went not into the details of the interaction between the graphene and the water vapor present in the air. So it's something that we have to go deeper in order to understand why this effect is produced. And with regard to the temperature, we are not interested in operating higher temperatures, because the final purpose of these graphene sensors is to operate at room temperature. So all the effort is focused on improving the sensing behavior at room temperature. Anyway, it has been proved that sometimes using the graphene, operating graphene-based sensors at temperatures above the ambient temperature is not, it does not lead to better results. In fact, also you must take into account that the graphene can decompose or undergo some kind of degradation when increasing the temperature. So in our case, we focus basically in the room temperature, because we work already in the lab with metal oxide gas sensors. And in this case, of course, we are more keen on in studying the effect of temperature in order to reduce as low as possible. But in the case of the graphene, the objective is to improve the sensitive behavior at room temperature.
Okay, thanks.
Thank you.
Thanks again for your very nice presentation. So I think we have no time for other questions. Sorry for the others in case they want to ask. So maybe we will move the discussion later at the end of the session. So it's now time to move to the next presentation. So Dr. Chakilam, floor is yours. So please share your screen. Okay, perfect. You can go.
Yeah, I'm Shashikanth, doing my PhD research from Kaunas Technological University. I am working on artificial biosensors. So in this conference, I am going to present my work on the morphological study of insect mechanoreceptors, which are going to develop the artificial bio-inspired mechanosensors. I'm working with rim guides. So this is my outline of today's talk, like objective, introduction, and physiology of the insect mechanoreceptors, which is the main part of that, and working and functioning of mechanoreceptors, the materials and methods, results and discussions, and our proposed model. So main objective is like we are going to study the morphology of the mechanoreceptors of an insect. What we have selected here is cockroach, but basically the morphology of the mechanosensors of all the like arthropods or any other insect. The basic morphology is same for all the things. So here there are different types of sensilla, that is hairs, but here we are selecting is trichord sensillas. These are being watched under scanning electron microscope and transmission electron microscopes, and we have done, and we have also studied the development of the sensilla components, and based on this morphological studies and sensing mechanism and material properties, so we have developed the artificial bio-inspired sensors. So basically the nature is the best example for development of any technology. So here insects has the best ability to sense even for the smaller flow or even in the smaller change in the environment. So that is the basic idea why we have selected this insect to develop the bio-inspired sensors. So here basically the previous researchers, what they have taken is they have taken the total sensilla as a inverted pendulum, and they have developed. So our main motive is to replicate exact morphological structure, and based on that we are developing the artificial biosensors. So that is the main concept. So basically this is the physiology of the insect. Like this is a hair, it is also called as seta, and this is the outer body of the layer which is called as cuticle, and this is the dendroid, or basically we can call it as a sensing element. So, and this is the joint membrana which is connected to this to give the support to this hair. So here this is a basic idea of this. So the basic development, how the hair develops, the mother cell is going to divide into two. One is the sensory mother cell, and this is the glycogen mother cell. So it again develops into two things, but one is trichogen and triogen, and this is the sensilla cell. So based on this mutations, so the one single cell, it will be developed into such part. So how this basic things works, like if there is any flow on the hair, the basic thing, suppose if there is a flow on this hair, so there will be two functionings will be done. One is called as coupling. It is also called as distortion of the tip of the dendrite. The second thing is transduction. That is a production of receptor potential. That means it takes the information till the brain. So that is these are the two things. Like if suppose if the flow is on the hair, due to this deflection, it touches this dendrite, and there will be the generation of the electrons inside that, and that will be taken to the brain. That process is called as transduction. Like coupling, the mechanical distortion of the cuticle produced by the bending of the hair must be touches this dendroid. This process is called as coupling. So it involves the distortion of the tips of the dendroid, which contains the tubular bodies inside, which is the main part to take this development of the ions from that surface to the brain. So inside this tubular body, there will be the microtubules, which is a which will be carrying these information. So this is a part. So transduction, the second part, as I told, the process involving in this deformation of the dendroid and the production of the ion potentials. So receptor potentials is a potential difference produced by this sensory receptors. Here the basic thing is like when there is a distortion of the when there is a flow onto this sensilla, there will be a bending of this hair. Due to this deflection, it will be touching this dendroid, and in this dendroid there will be a tubular body. So there will be the generation of the ions, and that ions will be coming down to this part, and that will be taken to the that information has been taken to the brain. So normally what we have done is basically we are selecting the insect, then we are seeing the we are taking the dimensions and the morphological structures by using scanning electron microscope, and we are cross-sectioning that to see the interior internal morphological of this structure by using transmission electron microscope, and we are analyzing that, and we are going to fabricate that. So this is our scheme of our research. So we have collected the insect, and we have prepared the samples by using sample preparation methods. Like we have taken a cockroach, we have anesthetized by you, and we have taken we have selected a particular antennal segments, and we have separated those antennal segments, and those are being treated with potassium hydroxide, and after that we have washed with ethanol. Then we have dried, and that sample we have taken those samples, and we have seen the structure by using scanning electron microscope. So here here on one single antenna, like so here you can see there are different types of hair on a particular antennas. So here if you see this in figure 1, these type of antenna, this is the sensillas, and this type of sharp pointed apex and little bit bulgy at the blunt tips, these are called as trichord sensillas. And in figure 2, the sharp edges, sharp pointed apex, these are called as basiconica sensillas. And the third thing which is distributed along the axis of the antenna, those are called as Ketica sensillas. So these are the 3 types of sensillas, but we are focusing on the trichord sensillas. But even so, that is a external morphology of an antenna, on which these are the different types of sensillas what we are getting. Now this is the interior part, internal morphology of a one single sensilla. See, these are the sensillas on the overall antennas with different types of sensillas, and this is the internal morphology of a one single sensilla, that is one single hair of the antenna. And here what we have taken is this trichord, this red color arrow, that particular sensilla we have taken, and we have done the we have dissected that. We have seen the sectional views, and this is the internal morphology what we have got. See, this part is the sensilla, that is hair, outer part what we can see on the antenna, and this is the cutica, what we can see on the body structure. And this black color, this This part is called as joint membrana, which is the elastic in nature. And this part is a dendroid, and internal part of this dendroid is a tubular body. You can see here. See, this is the in figure B. You can see this is the antenna, and this is the joint membrana. What this part, and this black total part is called as dendroid, in which there is a tubular bodies, and in that tubular bodies there will be a microtubules like round cylindrical structures, and this was totally protected by the socket septums. So this is the same thing till now. What a researcher they have taken is simply they have taken a like one straight hair, and which was directly taken with this springs as this joint membrana as a elastic part. So they have done. So what we are proposing is exact. We are replicating the same as the internal morphology is there. So here we have taken the blend hair with blend tape, and we are taking the joint membrana, as this joint membrana is developing from this base of this to give the support to this hair. And this is the dendroid, in which there will be a tubular body and microtubules. So this is the sensing element. This is the main sensing element what we are seeing. And this is the socket, and this one is the socket septum, which will be attaching the total part. So this is a tubular body, and these are the dimensions of our thing. So we have taken like the long axis of the socket is 5 plus 0.5 micrometers, and the short axis of the socket will be 4.4 plus or minus 0.5 micrometer. Then the length of the hair is 15 micrometers, and the diameter of that hair is 900 nanometers. The dendroid, the diameter is 600 nanometers, and in that the tubular bodies is of 500 nanometers, and the length of the each dendroid is 850 nanometers, and the microtubular which are inside the dendroid is 50 nanometers each. So I'm sorry. So the materials what we are considering, these are the exact materials what we are getting in nature. So we are trying to get the exact materials, but we are still working on it. What are the best materials we can select, and to develop the artificial mechanoreceptors which are exactly replicate the things. So our conclusion is, like, we have studied the functioning and morphology of the internal and external structures of the sensilla, and we have proposed the artificial mechanosensors model, and now our further work is to stimulate these things and also to develop the mathematical models but for this flow and tactile parameters. And mainly this can be used in any other any medical applications, and also even in smart watches, or even in our cell phones to use this scanning like so. This is my work.
Okay, thanks, Dr. Chakilam, for the very nice presentation. So we move to a very different perspective as compared to the former presentation. So very nice. Is there anyone in the audience willing to ask anything? Alberto, I see you're raising your hand, so please.
I'm just curious about how far are you from...
So sorry, we don't hear well.
Okay, it's a new
okay,
microphone.
Now
okay, now it works, sorry. I'm just curious about how far are you from the realization of a real prototype?
We are, as I told, we are trying to make exact replica of this model, as we can see. The proposed model is this, and we are trying to make exact replica with why, because the here we can do, and the structure will be the same. The joint membrane will be the elastic material. So I think maximum we can have this. We can,
Okay.
Okay. Thanks.
Okay, thank you.
Thanks.
Thank you.
So if no one else, I have one. So you mentioned in the next slide that so the basic working principle you're assuming to use is a piezoelectric one, right?
Yeah.
So my question is, so do you see any kind of chemomechanics mechanism in the working principle? So, I mean, do you have to consider maybe the transport of anything, can be ions or whatever, which is kind of typical if you have to consider so living tissues and so in a situation like the one you are facing?
Basically, as this socket septum is totally of fibroelastic materials, so as the basic principle how it works is, suppose if there is a flow on this on the external structure, so it will be deforming. So as this dendroid is touching, it is near to this structure. So it will this dendroid will be getting the deformation part, and as there are some tubular bodies will be pressed, and in that the ions will be generated in this tubular body, and that will be passing through this, through the micro tubular parts. So this is the basic functioning of this sensilla. So, but here actually we have taken this flow sensillas, but there are different types. See, if you see here, this smaller part like dome shape, this smaller part. So these are like tactile sensillas. Like these will be working for this pressure part, but the internal structure is the same. And even there are sensillas like which will be affecting, which will be seeing this even the chemical changes also in the environment. And for that there are different sensillas, like these are this part chaotic sensillas will be sensing the chemical changes in the environment. Suppose if any insect feels that there is a hot, there is a fire nearby, so it will be sensing that and it will be staying away from that. So those things will be sensed by these different types of sensillas. Here, this trichord sensilla, main purpose of this is to feel the flow and tactile part. So this is the this sensilla what we are selecting is basically for flow and tactile. But we can also, there are different types of sensillas based on different things, like chemical chemosensors are there, even pressure sensors are there. So this is the part.
Okay, thanks again.
Thank you.
And thanks for the very nice presentation. So I think again we're running out of time, so we have to move to the next presentation by Dr. Steffen Hadeler. And so Steffen, floor is yours.
Thank you. I hope you can see my presentation.
Yes, perfect.
And then I will welcome you to my presentation about the transfer printing of conductive thin films on PDMS with soluble substrate for flexible biosensors. My name is Steffen Hadeler. I finished my mechanical engineering the last year, and I work at the Institute of Microproduction Technology. The institute is located with 7 other institutes of the Faculty of Mechanical Engineering in the Center of Production Technology of the Leibniz University of Hanover in Lower Saxony, which is in the north of Germany. Some interdisciplinary research of the Mechanical Engineering faculty in the field of medical technology is possible with the medical school, which is also located in Hanover. And now I want to start with the state of the art to explain the background of my work. Various sensors in medical technology have conductive structures such as the cochlear implant or electrodes for electroencephalography. The manufacturing processes for all of these implants and biosensors show further potential for improvement, be it to increase the resolution or to reduce the manufacturing effort. Microtechnology has a great potential for improving these manufacturing processes and the performance of these implants. However, these materials used are not always biocompatible or require complex production steps. In my presentation, I want to focus on the electrocorticography. The electrocorticography is an invasive, highly sensitive measurement of brain functions, and it is used for treatment of diseases such as epilepsy or Parkinson, or as well in brain-computer interface, for example, for the control of prosthesis. The commercially available electrodes for the electrocorticography are made of platinum wires and plates in a PDMS, and the electrode spacing is about 10 millimeters. The advantages of these structures is the long-term clinical experience of the PDMS. But the disadvantage is the stiffness and the limited resolution of these electrodes. So there are various research groups who are working on high resolution electrodes, but these are mostly produced by photolithography and physical vapor deposition on polyamide. One example can be seen on the right. The advantages of these electrodes is the high resolution and the small electrode spacing, but the disadvantages are the complex production in a clean room and the lack of long-term clinical experience compared to the PDMS. In my work, a new manufacturing process for the production of the conductive structures on PDMS was developed. I wanted to combine the advantages of the above mentioned methods, and these are mainly the long-term clinical experience of the PDMS, the high resolution, and the small electrode spacing due to the PVD process. In the following illustration, I show the manufacturing process schematically. First, a PVD coating is applied on a water-soluble transfer substrate of polyvinyl alcohol. Then the conductive structure is contacted for evaluation using conductive epoxy and wires, and after that it is embedded in PDMS of the type Silgard 184. After curing the PDMS, the transfer substrate can be dissolved using only water, and the contacted conductive structure remains in the PDMS. Finally, the certain areas can be isolated in the PDMS. For the evaluation of the developed production process, various investigations were carried out. And here I would like to present only a selection of the experiments carried out. And these are subdivided in the material characterization, conductivity, and construction of a demonstrator system. First, I would like to start with the material characterization. The adhesion of these structures transferred from the transfer substrate of polyvinyl alcohol to the PDMS was tested in a cross-cut test according to the norm, and samples were prepared and evaluated with platinum and gold. In this test, the platinum coating was stripped from the PDMS much more easily than the gold film. Thus, gold has a higher adhesion to the PDMS after transfer from the PVA. This observation can be explained by the different surface energies of the materials, and the transfer process to the PDMS occurs with platinum with significantly more defects, since the adhesion to the transfer substrate is high. Based on all these results of the adhesion test, all subsequent investigations were carried out only using the gold as the coating material. After this, a tensile test was performed to examine the flexibility of the conductive coating, and it was examined at which elongation a conductivity of the coating is guaranteed. And different layer heights were tested, and the influence of silicatization was investigated, because silicatization has shown to improve the adhesion of polyamide to PDMS. As shown in the figure, the conductivity is given at the lowest of the tested layer heights up to an elongation of about 5%. The other investigated layer heights reach elongations of about 10%. And silicatization does not improve the flexibility of the conductive coatings. Following the material characterization, an electrical characterization was carried out. In a 4-point measurement, the conductivity of the coating before and after the transfer to the PDMS was evaluated in different layer heights. It should be investigated whether the transfer has an influence on the conductivity, and whether the layer height has an influence on it. In the right figure, the measured resistance before the transfer are shown in red, and the resistance after the transfer to the PDMS are shown in gray. And it can be observed that at the lowest tested layer height, a significant increase of the resistance was measured, but from a layer height about 125 nanometers, a defect-free transfer to the PDMS is possible, and no significant increase of the resistance was measured. Based on all these results, all subsequent investigations were performed with the layer height of 125 nanometers. After the examination of the conductivity, and electrochemical impedance measurement was performed as described in Navi's publication. And the test was performed in a sodium chloride solution with an LCR meter. And for this purpose, an electrode consisting of 2 electrode contacts with a dimension of 1 millimeter was manufactured, which can be seen in the illustration on the right. And also we can see the impedance over frequency on the right, which shows the typical form of these curves. With all these results, a demonstrator system should be developed. For this purpose, an ECOC electrode array consisting of 8 electrode contacts was manufactured on PDMS using the developed manufacturing process. And it is shown on the right figure. All 8 electrode contacts are fully functional, and electrochemical impedance measurements have been performed. Because the patient specific manufacturing of electrodes is also part of current research. The transfer process to three-dimensional shapes was investigated. For this purpose, various casting molds were manufactured additively using an FDM 3D printer. One electrode array produced in this way can be seen on the right. And we also tested different other forms of the casting molds. And there are no defects when transferring the thin film to the three-dimensional form. Now I would like to come to a summary. And in this work, a manufacturing process for the fast transfer of the conductive structures to PDMS using biocompatible materials was developed. I only use water-soluble transfer and the PVD process. Several investigations were carried out to improve the adhesion, the flexibility, or the conductance of the system. And finally, a demonstrator of an ECOG electrode array with 8 electrode contacts was built, and the transfer to the three-dimensional shapes was shown as well. Now let's come to an outlook, and the developed manufacturing process can be further developed in the future. For example, the use of high resolution mask or the roll-to-roll process is still of interest. The roll-to-roll process could enable the fast manufacturing outside a clean room, and the three-dimensional manufacturing can be investigated as well further with the use of higher resolution 3D printers, and so we can build patient individual electrodes. The adaptation of the manufacturing process to other implants or biosensors will be also investigated. Now, thank you for your attention, and I'm looking forward to your questions, and you can also send me your questions by email. Thank you.
Okay, thanks, Steffen, for your nice, very interesting presentation. And now we are open for discussion. So, any questions? Alberto, you have. Okay, thanks. Please.
Thank you. At the very end of your presentation.
The mic.
Okay. At the very end of your presentation, you have shown a result concerning the measurement of the impedance. It's not clear if this is the electrode impedance or it is the impedance of the solution or what else?
We did this test like it was shown in the publication, and it is the impedance of the electrode in the sodium solution.
Okay. And is there a reason you performed the test up to 100 kilohertz, so at very high frequency concerning the application that is for brain monitoring?
No, it was only to show what is possible with using the LCR meter.
Okay, okay. It's okay, thank you.
Okay, thanks.
Thank you.
Thanks, Alberto. Thanks, Steffen. So maybe I have one if
yes.
No one else is asking. Yeah, I don't see even in the chat no questions. So you mentioned the test done in order to check the adhesion.
Yes.
So a question can be, so how much can you stretch the polymeric substrate before having a crack? So, I mean, what's the limit you have using either gold or platinum or whatever before cracking?
Yes, as I showed, the thin films from about 125 nanometers on the PDMS I can stretch it about 10%, and the conductivity is still working. And by using smaller layer heights, the elongation of about 5% is possible.
Mm-hmm. Okay, so in the range, so maybe 10 is the maximum,
yes,
or is kind of threshold. So if you stay below, everything is perfect. Mm-hmm.
But after the elongation, and even over the 10%, after going back to 0%, the conductivity is working because the cracks are going back together.
Mm-hmm. Yes, but maybe you have a different response, I guess. Yeah, okay, yeah. No, because I was thinking of ISO sometimes for flexible electronics, they use a kind of hierarchy in the geometry in order to overcome the problem related to the stretching of the metallic film. So maybe that would be a way to go even further.
Yes,
I don't
we
know.
also tested some different forms of the conductive film, like some meander, but we had some problems sputtering on the transfer substrate using different forms. So this was used by the basic straight line.
Okay, thanks.
Thank you.
Any other? So I don't see anyone else. So I thank once again, Steffen, for the very nice and interesting presentation. And I think it's now time to move to the last presentation of this session by Dr. Chakkarapani. Please, floor is yours.
Okay.
So you can share your screen.
Okay. Right. Okay.
Perfect. Thanks.
I'm Ms. Lakshmi Devi Chakkarapani. I'm doing my research at Donau University Krems under the guidance of Professor Martin Brandl. Here I'm going to present one of my research work, carbon screen printed electrode coated with polytoluidine blue as electrochemical sensor for detection of Tyramine. Our intention is to develop screen printed electrode with a different kind of a polymer coating. And then with this electrode, we want to detect different kind of bioamines. So here I'm going to tell you why we need to develop this electrode, because sensor is a device which help us to convert the result in the form of signal. And our intention is to develop the electrode in the form of sensitivity, selectivity, easier fabrication, utility, and low cost, because we think the sensor has no generation-based miniaturization in the portable device and analyzed with micro volume of sample and fast electron analysis, and also lower production cost. The electrochemical sensing has a great impact, and it's also analyzed by different kind of method: potentiometric, voltammetric, conductiometric. From the result, we could analyze the electrode has a selectivity, specificity, interference, and also reusable, renewable, disposable, and size of the sample, and also the size of the sensor, and response time, real-time response, periodicity of the measurement, calibration, periodicity of calibration, concentration range, accuracy, repeatability, and reproducibility. This sensor is also help us to convert the chemical and biochemical activity into analytically useful signals. So why we need to analyze this kind of bioamines? Because this bioamines is also the biogenic amines. It has a great impact with the human body. For example, it can causes some serious health issues when the concentration is increases. And it's also involved some reaction with the human brain activity, regulations of body temperature and stomach pH, gastric acid secretion and immune response and cell growth. And somehow we need to find the way to control the level of bioamines in our human body. So that's why we developed this kind of electrode. There is many methods available in the society to analyze the bioamines, but the problem is these methods are really expensive. For example, chronoamperometric method or HPLC. This would be a need more time to analyze it, and the result, it won't be that much accuracy. And then the purification and the extraction is also need time. So that's why we want to analyze these bioamines by using electrochemical technique. The image one shows some kind of biogenic amines. And then there is many food contain these bioamines. For example, seafood, fish, meat product, milk product, and some fermented product, for example, beer and wine. But our body needs the lower concentration of bioamines, but when the level is getting increased, and it can causes the health issues, for example, headache, hypo and hypertension, and nausea, cardiac disease, and health, finally the death. So that's why we want to know how much the concentration of bioamines is present in our body. So when we have the health issues, if we go to the hospital and the doctor want to know which level of bioamines you have it in your body. So we hope that this electrode help for the medical purpose to analyze these bioamines and also give the right treatment for the patients. And the thing is, we use many kind of polymer and then metal complex nanomaterial to develop the electrode surface, because unmodified electrode surface doesn't have a desirable electron transfer. So that's why we want to develop the electrode surface, and then different kind of methods are available for this technique, like improving the surface. For example, electropolymerization and deep coating, drop casting method, and deposition, spin coating, and then layer by layer coating. The nanomaterial and the graphene and then metal complex, this kind of mediator develop the electron transfer reaction between the electrode surface and then the solution, like electrolyte with analytes. So here you could see we represent the screen printed electrode here. Substrate could be ceramic. So we use ceramic as a substrate, and then the electrode being printed over the substrate. So this chip include 3 electrodes, like a working electrode, reference electrode, and then counter electrode. So we don't need any other external thing. We just need to put the solution over the electrode surface, and then it's really easy to analyze. So that's why we take these electrodes for our research, because it's really simple method that we don't have to buy any external electrode, and then time consuming, and then we don't wait for the great instrument, like expensive instrument, because it's also really cheap, like 100 electrode would be cost some few hundred euros. So that's why we took this electrode, and then the leads help us to connect the electricity with the electrode. And then we use a polymer material. Here I mentioned different material. It's possibility to use this material, but in our case, we selected conductive polymers, polytoluidine blue, and we just drop case the monomer solution over the electrode surface exactly, and the working electrode surface. The working electrode manufactured, like printed by the carbon ink, and then also the counter electrode is printed by carbon ink, but the reference electrode would be silver chloride. After the polymer coating, the electrode is connected with the instrument, and then the instrument is connected with the PC. There we could see the results, and then we could use this result to confirm how much the analyte is present in the electrolyte solution. This is our working technique, like this is how we do the research. And then here you could see the cyclic voltammetric response of the polymerization of polytoluidine blue. So we put 1 millimole toluidine blue in phosphate buffer solution, pH 7.4. So we use unmodified carbon screen printed electrode. You could see 2 redox peak appeared. One appeared at -0.3 volt and Y1, And the another redox couple appeared at 0.0 volt, B and B1. So when we use the polymerization method, the toluidine blue monomer start to create a monomer radical, and then this radical bind it together one by one, and then finally we could get the polymer form because of applied potential and the current. And the A and A1 represent the monomer of toluidine blue, and B and B1 represent the polymer peak. The first cycle doesn't shows any polymer response because initially we can't get the polymer film. And then 30th cycle, you could see the B1 shows higher current response at 0.0 volt. And finally, after we get the polymer electrode, we just take it out from the instrument and then wash it with distilled water, because in order to remove the monomer particle from the electrode surface. And then we use this polymer electrode to analyze tyramine. Here I have represent the cyclic voltammetry response of modified electrode and then bare electrode in presence of tyramine 57.76 micromolar in phosphate buffer solution as electrolyte. The pH is 7.4 and the scan rate is 50 millivolt per second. We represent the peaks here. The black one is a bare carbon electrode, screen printed electrode in presence of a phosphate buffer solution. It doesn't shows any peak response. And then the red curve represent the carbon bare electrode in presence of tyramine 57.76 micromolar. And the blue curve represent polytoluidine blue screen printed electrode in presence of phosphate buffer solution, and the green one represent the modified electrode in presence of 57.76 micromolar tyramine in phosphate buffer solution. So here you could see the oxidation peak of tyramine appeared at 0.65 volt. When compared to the bare electrode, the modified electrode shows the sharp peak of tyramine with a high current response. But the bare electrode doesn't show the sharp peak, and then the current response is not countable. So that's why we feel that the electrode is capable of sensing tyramine. And then we use this polymer electrode in order to analyze tyramine with a different concentration. For example, we add step-by-step addition of tyramine, and then we analyze the current response. So from this figure 3, the tyramine concentration 3.6 to 57.76 micromolar in phosphate buffer solution, peak at 7.4 and the standard 50 millivolt per second. Here you could see the figure A shows the small a is the modified electrode. It doesn't shows any oxidation peak at 0.65 volt. Because we didn't add it in the first time, and then we B to K represent the different concentration of tyramine. It's added slowly, step by step. So each addition shows the high current response at 0.65 volt. So the calibration plot, the linear calibration shows the concentration of tyramine versus the current response when the concentration is getting increased, and the current is also increased because the current and concentration of tyramine is directly proportional to each other. We also use different pulse voltammetry technique in order to analyze the electrochemical oxidation of tyramine, because when compared to the voltammetric, like cyclic voltammetric technique, DPV method is high sensitive, and here you could analyze really, really lower concentration, like nanomolar concentration of analyte. So in this result, we have analyzed 0.2 micromolar to 16 micromolar range of tyramine in presence of phosphate buffer solution, peak at 7.4 and the scan rate 50 millivolt per second. So the first addition should be 0.02 micromolar, and then it started getting increase after each addition. the calibration plot represent the DPV response of the oxidation peak 0.65 volt, the current response, also the concentration of tyramine. And then we use this electrode for the interference studies, and we have selected the chronoamperometric technique for the interference studies. Here you could see we fix the timings 0 to 600 seconds, and then each 60 seconds we will add the tyramine. And the first 3 addition, you could see the gradual increase because we added 5 micromolar tyramine solution, and then you could see we selected dopamine, L-cysteine, butyrosine, and then histamine. It's 160 times higher concentration when compared to tyramine, but it doesn't show any current response. So it means this analyte doesn't have interference in towards the deduction of tyramine. And then again, we added the tyramine 3 additions. So it means this electrode has a high selectivity in order to detect tyramine, because we don't see any interference effect with this study. So that's why we feel this polymer electrode has a good sensitivity and also the selectivity. And finally, I have also used scanning electron microscopy and then AFM atomic microscopy, something like that, like in order to find out the surface morphology. And there we prove that our electrode is coated with a polymer, but I didn't show this result here, but somehow we use the different kind of technique to analyze the surface, and then we use the modified electrode for the tyramine addition. The future work should be planning to detect various kind of tyramine by using the polymer coating electrode, for example, butyrosine and then histamine. It's also the important bioamines which can cause a serious health issues. That's why we wanted to analyze it. It should be the future work. That's it. Thank you.
Thanks. Thanks for your nice presentation. And okay, so again, we are open for discussion. So we have a few minutes before the end of the session. So I think we have time to ask many questions. Anyone? So in the meantime, since I don't see anyone raising hands, so I have curiosity. So looking at the calibration plots you provided, so we see that so a linear fit is always very good, because I see a squared is always very close to 1. So are the results coming from a single test or
no,
by repeated times?
Multi-test. I didn't add the error bar.
Yeah, that was my question. Yes, in fact.
Yes. I should add it, but these results are I didn't thought to add it before, but the test is not just a single one. Like I made it 3 to 4 times, and then I concluded it, and then we put the calibration plot. Somehow, like later for the publication, I could add the error bar.
Okay, thanks.
Okay.
And still regarding this, so was it expected to have a linear calibration? Because I mean, even in the linear one could be not a problem. So you can even embed a kind of machine learning tool in order to learn the results and then set everything appropriately for the calibration. But so the question is, was it expected to be really linear in this frame?
Yeah, like we don't use just a single technique to get the calibration. We also use the cyclical diametry method and then different pulse diametric method. I also done the step-by-step addition with the chronoamperometric method. So we could get 3 different types of calibration plot. but I didn't add everything in this presentation, but somehow I will include the error bar for the future presentation or else for the publications. But we don't take just one calibration, like we use different methods. Mm-hmm.
Okay, thanks.
Okay.
Any other questions? I don't see. Alberto, do you have?
Yes, Stefano, I have one.
Yeah.
Okay.
Yes, please.
Your electrodes are printed electrodes.
Yes.
What about the stability of your electrodes?
Stability after the polymerization, we run cyclic voltammetry for 100 cycle, because here you could see the current of polymerization somehow 100 microampere. But when we took this electrode for analyzed with the Tyramine, you could see the same current, like nearly 100 microampere. Mm-hmm. So how we get this stability? Because we use a cyclic voltammetry technique, and we just take the modified electrode and use the pass-speed buffer solution as electrode light. We run almost 100 cycle, and then we use this same electrode for the Tyramine analysis and then further studies. That's why we could say like it has a great stability. After the 100 cycle, it doesn't show lower current response. The current somehow stable. So that's why we feel this electrode has a high stability.
Okay, thank you. Mm-hmm. Thank you.
You're welcome.
Okay, thanks. Thanks again. Any other? I don't hear anybody speaking. So I think that's it. And so Dr. Chakkarapani, thanks again for your nice,
so much.
Very interesting presentation. And so I think it's now time to close this session. Yep. So my applause goes to all the speakers. It was really a pleasure to chair this session. So we saw very nice, interesting, diverse presentation related to this very interesting field of chemo and biosensors. So thanks for contributing. Thanks for participating. And let me just say, it's now, as I said, time to end this session and to have a break just for a while, because keep in mind that at 11 we will have the keynote lecture delivered by Benedetto Vigna. So just a few minutes to end this, and we'll be here again. Okay, thanks again for participating.